Thank you so much, Larry. It's a real pleasure to be here, speaking to you all and to follow in the footsteps of many great webcast presenters, lecturers over the last 20 years, as Larry says. I'm going to just share my slides now, so hopefully this will work for everyone. Um, so today's lecture is all about interaction effects. As Larry said, this is a major part of my own working life. And so I want to share with you today, starting with some of the more fundamental aspects of testing linear interaction effects, going on to talk in a bit more detail about how to interpret and probe these effects, and commenting on some of the good and bad habits that are done, and what I would recommend that you do in this situation. And then we'll look at various extensions to the linear interaction effects. In particular, we'll go to generalized linear models, to quadratic regression models, and then we'll touch on a few other extensions as well. So we'll start off by looking at these two-way linear interactions. Many of you will be familiar with testing linear interactions. You will almost certainly have read work which does it, whether or not you've actually tried it yourself. But it's probably just worth saying to begin with, we often use the term moderation. It's often used synonymously with interactions to talk about these type of effects, and broadly, it's the same type of thing, although there is a slight difference between them, in that moderation describes how a relationship between two variables, x and y, normally, how that would be affected by a third variable, which we'll call z. And I'll say at this point, because I'm British, we say z. I'm going to try and use the pronunciation z while I'm talking today, just for consistency. But if I slip up and say z, then please forgive me. Whereas an interaction effect more generally doesn't necessarily rely on some underlying relationship between two variables. It's just about how two predictor variables interact with each other. But most of the time, we do rely on theories where there is a relationship between two variables which depends on the value of a third variable, z, in the simple case. So in the example you see on the screen now, this is looking at the relationship between training as the predictor or x variable and job performance as the dependent or y variable. And what this plot shows is a fairly typical plot depicting a two-way interaction effect. It shows that for people who have a low level of autonomy, so that's a solid line, you've got a positive but not especially steep relationship. Whereas for people with high levels of autonomy, there is a stronger, more steep relationship. So it suggests that autonomy allows the relationship between training and job performance to become stronger. We talk about two-way interactions because it's the interaction between two variables. In this case, it's the independent variable x and the moderator z. But we'll look at situations later which involve more than just these two variables. So statistically, what does this look like? Well, again, if you've done any of this yourself, this will look familiar to you. But it relies on an equation. A normal regression equation with one predictor variable would be something like y equals a plus bx, where b represents the slope of the relationship, or the strength or effect size. There are all sorts of different ways we can describe it between x and y. But for a simple moderated regression model, it looks like this. We have got y being a function of an intercept a, then plus b1x. So b1 is the regression coefficient for the variable x, or what we often call the main effect of x, plus b2z, so the separate term for the moderator, and then plus b3 xz, where xz is the multiplicative interaction. In other words, just the product of X and Z, one multiplied by the other. And B3 is the moderation effect. Generally speaking, if B3 is significant, that means we would say there is significant moderation, and we would want to go on and interpret this. And just if you're wondering, that Greek letter at the end, epsilon, is what we often use as a residual. So that's not a part that we would interpret, but it's part of the model that would be estimated. So B3 represents the moderation effect. If it was that simple, then we wouldn't have to have a whole lecture on something like this. But it can't be interpreted in isolation, unfortunately. We need to also consider B1 and B2 to get the full effect. And we'll talk about what we mean by that in a moment. But you may be wondering why we look at the multiplicative interaction, the product of two variables, in order to test moderation. Well, it can be shown by rewriting the equation that you see towards the top of this slide instead as the equation you see on this slide. This is the same equation, it's just rewritten. It's reorganized so that we've got, in the first set of parentheses, a plus b2z. That is equivalent, if you think of z for the moment as just a number, that's equivalent to an intercept. And in the second set of parentheses, b1 plus b3z, that's multiplied by x. So that's equivalent to the slope or gradient of the relationship between x and y. And what you see here then is, if we think of this as a straightforward linear effect, both the intercept and the slope are themselves depending on the value of z. So by having the b3z in the second set of parentheses as the way that the slope is depending on z, that is the moderation effect. That's telling us how z affects the relationship between x and y, affects the slope of that relationship, that is. And so we don't usually estimate it like this. We usually estimate the terms separately, as I showed on the previous slide, but it can be helpful to think of it as this, especially as, if you note here, if z is equal to 0, then the slope of x is just b1. So that's a really important thing when it comes to trying to interpret the results of an interaction effect, as we will see in a few minutes. So how do you go about testing this? Well, I'm not going to speak a lot in today's lecture about doing things in different pieces of software, because I'm sure that lots of you use different software. From experience of doing previous sessions, I would imagine that there's quite a lot of you who would use one of these three packages, though: SPSS, R, or Stata. This is just example syntax for how to test a straightforward two-way linear interaction, such as the one showed on the previous slide, in each of those pieces of software. In R, there's various different ways you could go about it. I will say a little bit more about that in a moment, but in SPSS, in fact, in SPSS2, there's different ways you can go about it, but this is probably the most straightforward way. SPSS is slightly different from the other two in that you do need to calculate the interaction term separately if you're using the regression procedure. Whereas in R and Stata, you can do it automatically as part of this procedure. I should say, by the way, in case this prompts any questions, I'm not myself a Stata user. I probably won't be able to answer any difficult questions about Stata, but I'm reliant on my friend and colleague Mikko Ronka, who does use Stata a lot and has supplied some of the Stata syntax for the work that I've done with him. So this runs the regression analysis. This produces a table of regression coefficients in the way that you'd get for any regression, including testing whether that B3 term, the interaction term, is significant. So let's assume for the moment that it is. How do we go about plotting that? Well, plotting it is the first stage that we would want to do in terms of interpreting the interaction. It might be the only stage we need to do, but even if it's not, it's almost always the first stage. Some software will do this automatically. So if you're using R, you can use the marginal effects package and the plot underscore predictions command. There are all sorts of other packages in R which will allow you to do that. It's not the only one, but it has certain advantages when it comes to some of the uh, more sophisticated interpretation. In Stata, I'm informed that you can use the margins command with the plot function. But if you're using SPSS or another software that doesn't allow you to plot it automatically, I've got some Excel tools on my website, the address of which you see there. And these tools allow you just to take certain bits of the output, type them or copy and paste them into an Excel template, and it will produce a plot for you, such as this one here. This is on my website. It's a, a plot, a very generic plot called two-way linear interactions. And in this, you would enter the variable names, you enter the coefficients. You can either enter the means and standard deviations of the variables or choose the values at which you will plot the slopes. I'll say a little bit more about that in just a moment. You can also choose to put in alternative labels or legend for the plot too, but it will produce a plot which looks a little bit like the one you see on the slide at the moment. And then being able to interpret that becomes relatively easy. The more you do of it, the easier it will get. So in this case, this is a relationship between work demands and job satisfaction, and we see that for both high and low values of training, this seems to be a negative relationship. But at high values of training, it's a relatively weak negative relationship. And indeed, you might want to ask further questions about that, which I'll come on to in a moment. Whereas at low values of training, it's a stronger negative relationship because we see that the line there is steeper. Now, just before I talk about some further probing that you can do of this relationship, there are a couple of questions that it's worth addressing because these come up very frequently.